Welcome, everyone, to another episode of Vision Basic. It's been a couple months since my last video, but as usual, I've been quite busy. I'm still chugging away on version 1.2 of Vision Basic, but the code I'm working on is fairly complex, and I'm not able to execute it for testing until I've pounded out the code for the entire routine. It's also tax season, and there's a lot of prep work that goes along with that. And I got my first colonoscopy done. Fortunately, my insides look good. I'd share the photos with y'all, but I'm sure someone would complain. The experience wasn't as bad as I was expecting it to be, so if you need to have it done, please get her done. And my cat got knocked up and had herself a litter of kittens, but they're all cuties, 3 of them. We have a couple of folks who are interested in the boy kittens, and we're probably going to keep the girl kitten. Unfortunately, Mama Cat just went into heat again just 7 weeks after giving birth, so we've got the house locked up super tight. She's getting on every nerve we have, but we're desperately trying to avoid ending up with more kittens on our hands. I had a couple topics planned for my next 2 videos, but I decided to focus on something a bit more fun for this video. So today I'm going to show you how to open up the top and bottom borders using Vision Basic. There is a lot of information out there about how to do this, and I'm no expert on this topic, but I managed to figure it out, and so I can share my experience with you so that you won't have to stumble through it like I did. I'm not going to cover the removal of the side borders in this video. I'll try to figure that one out if I can, and if I do, I'll make a video about that down the road. In order to prevent the top and bottom borders from being drawn, you have to trick the VIC chip into thinking that it has already started to draw them. Now let's stop this screensaver for a moment. The basic idea is that before the raster beam reaches the bottom border, down here, we need to change the screen over from 25 visible screen rows down to 24. We need to do this at the proper time though, pretty much right before the raster beam attempts to start drawing that bottom border. You might wonder why anyone would need to shrink the screen down to begin with, but when you try to perform a smooth scroll of a text screen, you need an extra row of characters, and the 1K area taken up by the text screen does not have room left for that extra row of characters. To scroll a screen vertically, you would need 26 rows of characters, and that would require 1,040 bytes of data. But that would require the text screen to bleed over into the next 1K area of RAM. You would need that extra row of characters because, as one row starts to vanish from the screen, a new row gets revealed at the opposite side of the screen. Let me show you what happens when we try to scroll the screen vertically. Poke, 52281, 14, penny, 0, and key press. Here you will see some junk at the top of the screen. Right here, junk. I had to change the screen color because this extra junk usually appears as black pixels against the background, and our background in Vision Basic is black by default. And this renders the junk pixels invisible, but only on a black screen. Since we can't have 26 rows of character data, and since the row that does open up tends to show junk pixels, we need to hide those junk pixels by reducing the screen down to 24 rows. But this isn't a video about scrolling the screen. Those junk pixels, though, are an important thing to note. And we'll get to that further into the video. So what does it look like when we reduce the rows from 25 down to 24? Let me demonstrate. And I'm going to paste in some code here because it's kind of lengthy. Let's see, Alt Insert. Press Enter. First, notice how a regular screen looks. It hasn't changed at all. And now I'm going to press the Y key. And there you go. So like here we have 24 rows, and here we have 25. So as you can see, it kind of cuts off, like half of the top row and half of the bottom row. Now, to trick the VIC chip into not displaying these top and bottom borders, we need to change the row count from 25 over to 24 when the raster beam reaches to about here. right about here. I'm going to put the mouse here. And if I press the Y key again, you'll see that the border ends up being moved to a spot just above the raster line. And there you go. So when the VIC chip checks to see if it needs to start drawing the border, it will think that it has already started doing so. Since the top and bottom borders are really just a single border that wraps around from bottom to the top, the effect will continue all the way from the bottom to the top. And to clarify, this bottom border bleeds into the top border. They're both one border. Press in. I'm not going to go into extreme depth on how to pull off the effect of removing the top and bottom borders. Rather, I'm just going to loosely explain the program I've written, and all you need to do is copy some of the code into your own programs. As a bonus, you'll get to see how easy it is to set up interrupts in Vision Basic. Before I show you the code, let's run my program again, but without the top and bottom borders. Unlike what you saw at the beginning of this video, our borders are now gone. I changed the background to gray in order to show you the junk I was talking about earlier. The top and bottom border areas are full of it. I'll explain how to deal with that in a bit. The blue lines rising up on each side of the screen are just showing where the raster line is when the sprites all get relocated for movement. Since the borders have now been removed, there is no single raster line that is consistently suitable for moving all of the sprite shapes at. This is something I discovered when learning how to remove the borders. Normally, I would choose to relocate all of the sprites when the raster beam is drawing the top and bottom borders to help reduce flickering. But now we have no top and bottom borders. The flickering tends to happen when your sprites are moving up the screen. If you move the sprite upward as the raster beam is about to meet it, you'll see a flicker. The sprite vanishes for a tiny moment. If you want to remove the borders in your own programs, but you're not proficient in assembly language programming, you might have to allow your sprites to flicker a little bit here and there. My solution here was to follow the sprites upward and only relocate them at a point just above the sprite in the second row, the cyan one. But since all of the sprites that are moving upward are evenly spaced, I use the location of the cyan block and perform a calculation on it so that the raster beam is only caught in a narrow band of rows. If you follow the blue line, you can see that it stays ahead of the cyan block first, and then the green block, and then the yellow block, and finally the brown block. There are some raster lines that you don't want to catch using the catch command, because some values will cause the beam to be caught in two different places on the screen, due to a limitation of the catch command. This is more likely to happen on PAL systems because those systems provide a wider range of raster values. Now I'm going to pause the screen and show you how this line stays ahead of the sprite shapes. Okay. Now notice it's just ahead of this blue one, and so all of the sprite shapes are being moved at this very specific moment here, just ahead of this cyan block, and then now you can see that it has shifted back down and it's staying ahead of the green one. And now it is staying ahead of the yellow one. And finally, the brown one. As long as it's moving the sprites before they're actually drawn, and you know, if they're going upward anyhow, there shouldn't be any flickering. My program uses a rather slow method of calculating a good spot to relocate all of the sprites, but an assembly language routine could find an ideal raster line much more quickly, and thus not slow down a game program that you might wish to remove the borders on. And again, this is all about trying to prevent your sprites from flickering. But despite using a slow calculation, it's fast enough to get the job done for this demo anyways. Let's go ahead and take a look at the program. In line 10, I'm clearing all variables, and I'm defining two tags that will be used as pointers to a couple of interrupt routines. In lines 20 and 30, we're moving the text screen to the last video bank of the 4 available. This is necessary because we can't pull off this effect on the regular text screen, at least not in Vision Basic. I'll explain why here in a second. Line 20 copies the character set to this last bank, bank 3. Our new text screen will reside at location 52224, and the character set will be hidden beneath a layer of VIC registers and character ROM starting at location 53248. We are setting some screen colors in line 40, but we are also poking a value to the last memory location in the C64. Right here. See, the garbage you saw earlier in the upper and lower border gets its pattern from the last byte of the current video bank. You'll probably want to clear this byte out with a value of 0, but I wanted you to be able to see the garbage first before we eliminate it. So I actually poked my own pattern byte to the location, and in this case it's 85. The original pattern might vary by computer model and location. And heck, if it's already 0, then you may not even see it. Now, I'm not certain if this works on all models of the C64, but if you use a black background, you might not even need to clear the garbage byte. But since I don't know if this is consistent, I'd rather not take the chance. Before explaining the rest of the program, let's remind ourselves what the garbage looks like. Again, garbage, garbage. If you're using a text screen in the first video bank, bank 0, you'll need to poke location 16383 with a 0 to clear out the garbage byte. This is why you can't use the regular text screen in Vision Basic for this borderless effect, because you're likely to overwrite some compiled program code in the process, most likely a byte in the command support library. Anyhow, location 16383 is the very last byte of the first video bank. If you're using a text screen in the second video bank, bank 1, you'll need to poke location 32767 with a 0. I don't recommend using bank 1 to place a text screen in because you can still overwrite something important related to your program, at least in Vision Basic. And if you're using a text screen in the third video bank, bank 2, you'll need to poke location 49151 with a 0. It's always 0. And like I said, you'll need to poke location 65535 with a 0 for the final bank, bank 3. And of course, if you want some kind of pattern in your top and bottom borders, you can place a byte in the locations I've mentioned to accomplish this. It will have to be some kind of vertical stripe pattern, but it's certainly an option. Let's get back to our listing. Okay, so line 50, we're starting back up here, fills up a range of bytes that make up the data for sprite shape numbered 128, specifically within Video Bank 3. We're filling those bytes with a value of 255, which will essentially create a square shape, or square-ish. And I just didn't really, I wanted this to be a quicker video, and I didn't want to have to create a happy face or something like that. I don't know. Maybe I'm a little bit lazy. I just want to get this video out there for y'all. And, colored squares, come on, they're charming. Okay, lines 60 to 80 pretty much set up all of the sprites for this demonstration when it comes to shape and color. Lines 90 to 120 define the variables for our sprite starting positions. Line 500 takes a key press and will start the border removing interrupt if I press the Y key. Otherwise, the borders will remain intact. Line 510 sets the background to black if I choose not to remove the borders. Line 520 calculates the best raster line for sprite relocation. It's a bit messy, and I could combine 3 of those values into a single value. These values here. I was just toying around with various values and just kind of left the messy math in there. At the end of that line, we catch that raster line. It's important to note that you can't catch a raster line where an interrupt is happening, because it'll be waiting a very long time. Like forever. Line 530 increases the border color so that we can see when our sprites are being relocated. The border turns blue for a brief second when this happens. You saw this earlier. I'll explain line 540 later. And line 550 moves all of our sprites with a single command, and this happens at machine language speed. All mobs is a great command. Line 560 changes the border back to green by decrementing the color value. Lines 570 and 580 are responsible for all of the vertical sprite movement you see in the demo. The Y locations are either increased or decreased here. Line 590 will keep the demo running until a key is pressed. And line 600 turns off our border erasing interrupt and restores the text screen back to location 1024. This all allows for a clean exit from our program. This line turns off the interrupt, whereas line 500 turns on the interrupt. The first value you see here, 249, is the raster line we want to start our interrupt at. And the value of 1000 here is the line number of the interrupt routine itself, down here. Remember, raster line 249 is where we are trying to change the screen from 25 rows down to 24 rows, and this is how the upper and lower screen borders end up not being drawn. Some interrupts only need a single routine, but we need two different routines for two different interrupts that need to happen. Line 1000 sets the tag routine 1 here to point to the interrupt routine itself. Interrupts should usually start with the start int command, so this is why you see it in line 1010. Start int. Line 1020 sets the row count to 24 rows using a special poke of sorts. It's important to note that you must not use most basic commands in an interrupt routine. And if you hear a cat meowing outside my door, it's because she's in heat and she wants in. The reason for this is that our interrupt routine is probably going to interrupt a Vision Basic command or function while it is trying to do something. And if we interrupt a Vision Basic command or function to try to run another Vision Basic command or function, we will probably garble up important memory registers being used by the command or function that we are interrupting. A crash is bound to happen. There are a small handful of commands that you can actually use during an interrupt, but complex interrupt routines will likely need to employ assembly language instructions. Using the let command to set the value of a memory register allows beginners to program simple interrupts without needing to know assembly language. You can set border colors this way, or set up a screen that is half bitmap or half text screen, for example. For those who are new to interrupts, an interrupt is a means of interrupting the normal flow of a program to perform a time-sensitive task. You pick a raster line that you want to perform this desired task at, you perform that task, and then you return control back to the regular program that is currently being executed. Our program here requires two interrupts. Our first interrupt routine sets the row count to 24 rows at raster line 249, and our second interrupt routine sets the row count back to 25 rows at raster line 252. I can do another interrupt video down the road. This video is just meant to show you how to remove the top and bottom borders, so let's get back to that. Now, line 1030 sets the raster line that we want our next interrupt to happen. We could use the raster command to do this, but that command also pokes to register 53265, which has already been poked to in line 1020, right here. Actually, the raster command pokes both of these locations. And since our chosen raster lines don't exceed a value of 255, poking a value of 19 or 27 into register 53265 already takes care of that extra high bit, setting it to 0 instead of 128, which is exactly what we want. I'm not going to go into how the raster value is composed of 9 bits in this video. Perhaps another day. And line 1040 sets the pointer at locations 788 and 789 to point to the second interrupt routine using the tag routine2. And line 1050 performs our exit from the interrupt itself. Using a parameter of 1 with the int_end command forces a normal exit from the interrupt. So if you look at the second interrupt routine here, you'll see that it looks very similar to the first routine. The main differences are that line 2020 sets the screen row count back to the normal 25 rows. Line 2030 sets the next interrupt to happen back at raster line 249. And line 2040 sets the interrupt vector to point to the other routine, the first one. So the job of lines 1030, 1040, 2030, and 2040 is to set things up for the next interrupt. The two routines kind of bounce things back and forth to each other. So these lines here basically set things up for this routine, and then these lines here pretty much set things up for this routine. I'm pretty sure that you can get away with using just a single interrupt routine instead of two. You would just have to wait and catch raster line 252 and perform the poke you see in line 2020 before exiting. I mean, it's a little bit more complicated than that, but really you could use one routine. Oh, and the parameter of 0 following the int_end command in line 2050, right here, forces a jump to the key scan routine. This is important because you do need to have the keyboard scanned a single time with every screen refresh. There aren't enough raster lines between the two interrupts to have the keyboard scanned in time, so that's why we're having it done at the end of the second interrupt routine. Locations 788 and 789 normally point to the interrupt routine that scans the keyboard, but you can clearly see that we are diverting this pointer in lines 1040 and 2040. Right here and right here. If we don't divert things back to the normal routine pointed to by location 788 and 789, the keyboard won't be scanned and the clock will stop ticking. Alright, so let's run the program again before I make some changes. So what I want to do next is remove the garbage in the upper and lower border areas, and then change the screen to black, and we can eliminate the blue line that's zipping up the left and right borders. First, we're going to eliminate the garbage. We're going to change the garbage byte to 0, right here. Boom. And let's run it again. And see, no more garbage. Nothing here, and nothing here. Let's go back and make the other changes. And we're going to change this background to black by doing this. And we're going to get rid of a couple lines. The lines that cause the little blue line to show up in the border. And now we're going to run it. And there you go. Top and bottom borders removed, and sprites gleefully crossing those border areas where they are normally not visible. I've noticed that some programmers like to put static sprites in these border areas to show things like game scores and other game stats. You can't put character graphics there, so it's a neat little trick to get some artificial characters in there. Sometimes they use multiplexing so that they can retain 8 player sprites on the main screen area. But usually you'll see like maybe some score information or some other kind of stats down here in the bottom or the top. Either way. I do want to show you why it's important to pick a good raster line to move your sprites on. And we're going to put a rim here. And we're going to bring back our catch 50. And basically I'm trying to explain why. I mean, I've already kind of explained it earlier, but why we have this, we're trying to catch the line before the, in front of the sprites so that there's no flickering. Anyhow, I'm going to show you what happens when we just have a static catch here. I don't know if the recording will show this, but you should be able to see some flickering of the sprites that are moving upward as they cross raster line 50. This can happen at any raster line, but this program is moving all of the sprites at raster line 50. So if you watch this cyan one here, flicker, 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 flicker. And it just keeps repeating itself, so flicker, 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 flicker. If you're a beginner and wish to use this effect of having no upper and lower borders, you'll probably have to put up with an occasional flicker. I'll see if I can put together a routine for a future video that helps to eliminate this flickering. No promises though. Until then, time's up for this video. As usual, I thank you all for watching. Please like and share my video, and definitely subscribe for more similar content. And make sure to visit visionbasic.net.